שיעור השלמה אחרי שנגמר סמסטר.
אוקיי,
מה זה אומר?
למשל.
מה זה אומר על המטלה האחרונה? כאילו על תוכנת סיכום. ה-IDA.
Okay, that's actually something that we should talk about. As you know, the grade in this course is given based on your home exercises and another home exercise. Which is usually something that it is something that you can do using whatever you want. I need to though get the impression that you understand what you were doing. And usually give it something like 24 hours. So like, and let's put it like this, since it's a home exercise, one thing I would like you not to make it a group exercise, but I have very little ways to enforce that. And as far as I'm concerned, you can take that home exercise whenever you want and bring it back one day later. Whenever you want has to be, however, after I prepare it. So, and that I guess will be around mid-July. And how late can it be? Let's say no later than the 15th of August. So during that month, just send me an email if you want to start. There is, however, a suggestion between the 24th and the 29th of July. I'll be on family vacation. So, I don't know, well, depending on war, no war, I don't know, maybe. But currently the plan is to be on family vacation. So if you want to do it during that time, that's basically okay, but I will be less available to answer questions. That's it.
Where are we going?
What?
Where are we going?
Critical Austria. To the land of far, far away. Not that much. Okay, so today we started last time, which was quite long ago, to talk about interferometers, how they measure, and what are their limits. I'll remind you a little bit about the standard SU2 interferometer, and then I'll talk about most of today will be on a different kind of an interferometer, the SU1. And I'll remind you about the parametric amplifier, what it can and cannot do in terms of quantum optics. But so let's see better from here. Apparently I'm tired. I was about to write English right to left. Maybe not. Say SU2. Now most interferometers are passive interferometers, meaning that, and the standard way to think about them is to think about the Mach-Zehnder interferometer. Mach-Zehnder interferometer has two inputs, and then eventually it has two arms where it is convenient to think that one of them gets a plus phase and the other one gets a minus phase. Of course, it doesn't really matter because everything is interesting up to modulo 2 pi. And then we have outputs. So we can first do very quick analysis of what's the relation between the input and the output, because what we're going to do is to say something like, I have some state of light here, so here there will be some state of light that can be basically, I don't know, for example, it can be, say, alpha in mode 1 and vacuum in mode 2. That's a simple, very common state. But I can also make, I don't know, a state like this. N photons in mode 1 and N photons in mode 2. If you could make this state, now this is and of course those two states are very different. In this case you have exactly the same number of photons in both inputs. The other case, well, I don't know what the photon number in each output is, and in one of them there's nothing. So given that state, I want to be able to do all kinds of calculations. So like and then here, so now if I could write, so I can try to write psi out as something. I don't know, for example, I could try to write it this can be the eventually, I don't know, and those I call, here when I say 1 and 2 I mean the output ports, and here when I said 1 and 2 I meant the input ports. And just to explain, so okay, so if I could write that, where this is written in, so that would be like in the outputs. I don't know, I'll write here like B1 and B2. And on these ones, I'll write that this actually is for A1, this is for A2. So all I'm saying is, look, what happens here is that we are mixing modes, but all we're doing is some kind of a transformation eventually. What do I mean? Like, what I have here is simple. This is a beam splitter with reflectivity equal transmission equals. Then I could say, look, here you have 1 over square root of 2 A1 plus A2. So that is the annihilation of a photon here is related to a superposition of annihilations here and here. Because if you have a photon here, that means that it could have come from here or from here. So it is, but it's not just a probability, it's a superposition with a phase, which caused it to come in this side. And if it was here, then it comes with a minus sign. And then what happens? Okay, now we propagate. Now what will happen? Well, we'll acquire a phase. So here, because of the phase, I'll add also e to the I phi. And in here, due to the phase, I'll add e to the minus I phi. And then what? I combine again in the same way. So, if I want to, so the simpler way to analyze the interferometer is by actually not generating the output state, but actually, I'll show you in a moment how we can do that, but actually translating the operators back. So what am I saying? Well, you know, I can do the same. B1 equals what? 1 over square root of 2 of what? Well, 1 over square root of 2 A1 plus A2 e to the I phi plus 1 over square root of 2 A1 minus A2 e to the minus I phi. That's what. And of course, so you can, and clearly you can see, okay, there's going to be a half. So A1 is going, so this will be like A1 times cosine phi. I guess you see why. In the way it is written right now, then I'm going to have plus I A2 sine phi. Yes, I think that's true.
I think the exponents are supposed to be different.
What do you mean?
The A1 plus A2 is the minus, but
With the minus, the one
doesn't
that,
make any change.
well, maybe it flips the sign here, but to make things consistent, I'll give that one the plus. Here that would be a plus, and here it will be the minus. Now we're good? Okay. So, and of course, B2 will be, well, with a minus, so it will be A2 cosine phi, I think, minus, no, also plus, I A1 sine phi. Now, okay, so now I can do one of, given that's the relation between the output operators and the input operators. Now, it is important to understand why is that. And the reason is that okay, I'll explain. You know what? I'll explain in a moment. But so now what we have is we expressed the output operators in terms of the input. So basically now I can do one of two things. Now I can calculate anything, assuming that I know the state at the input. We're going to play with that state a little bit. So I can, I can calculate things like what is the average number of photons in mode 2. So that is what is that? That's the average of B2 dagger B2. Well, now I know how to calculate that. This is psi B2 dagger B2. And I can write, the point is that psi is written in terms of A's. So no problem, I can write it. That's what we did last time. This is a quick reminder. So I can say something like, okay, if this is, so I can write here psi at the input, and I'll express those in terms of the input operator. So I'll write something like A2 cosine phi minus I A1, sorry, dagger sine phi times, of course, B2 cosine phi plus I A1. That. And we can calculate that, given the state. But let me show you also how we can do the opposite. And that is, how we can calculate the output state. So, okay. So if I wanted to calculate what is the output state, I would do the following. I would write the state, so this is, now we can, that is, calculate in this case, I calculate any quantum quantity I want at the output, given the input state. But I can do also another thing, and that is I can say, look, let's look at this input state. Okay, this is, I think that 1 over square root of n 1 factorial. Or 1 over square root n factorial again. So let's just write it like 1 over n factorial. That's just and that is just simply A1 dagger to the power n times A2 dagger to the power n operating on the vacuum. That is the state. Now, what I'm telling you is, okay, we can use this transformation, I can invert it on its head. So I can also say, look, if I express the input operators in terms of outputs, then I can say something like, look, A1 equals, well, it's going to equal something exactly the same. B1 cosine phi plus I B2 sine phi. Due to symmetry, maybe the sign here will be minus, but that's not an important thing. Or, and then A2 equals B2 cosine phi plus I B1. You don't have to believe me, so we can invert this. And then I can write, so that's, if one option was calculate quantum quantities at the output given the input state, and then you would, this is express output operators by the input. The other option is find the output operator. I can do that. But that, I know what it is. Like in this case, it will be 1 over n factorial A1 dagger, but this is A1. So it is going to be B1 cosine phi plus I B2 sine phi. Now not plus, I'm going to take that to the power n and it's going to be a dagger. So there will be a dagger here and a dagger here and a minus sign here. And then this times what? Times B2 cosine phi minus I B1 dagger. Phi. All of that to the power n, and this operating on the vacuum. And we can calculate this and get the output state in terms of photon numbers at the output. Usually, that is here we express a dagger either way works. And I want to tell you, so first of all, why does all that work? Because a beam splitter is a Hamiltonian transformation. I can write the Hamiltonian of a beam splitter. And a beam splitter is a unitary transformation, so that I can say that there is the Hamiltonian of a beam splitter. And it is rather simple. So, okay, now usually we would say something like U equals e to the I Hamiltonian t. Now for a beam splitter, there's not really a time. We're not interested in the time passing through the beam splitter. So let's call that time 1. So I'll say that this is like e to the I h. And this Here we take and what we're saying is, look, that U so I can say something like psi out equals e to the IH times psi in, if this is a Hamiltonian situation, or I can say something like A out equals A in, and then e to the IH, and then e to the minus IH, like that. This is, the question is, and now is there a Hamiltonian that allows me to do that? And the answer is yes. The Hamiltonian is
Isn't it a matrix of 1 over square 2 times a matrix of 1, 1, 1 minus 1?
I'm not, I think it is. Well, wait. Let's just the A's and B's here are confusing, and now this is something that I didn't write before, and now I'm getting confused. So I'll write. Oh yes. I think that the Hamiltonian is A1, A2 dagger plus A2, A1 dagger. Now let's see, how would I, and now let's assume that I want to actually calculate that. Now what is the problem with calculating something like this? So let's say that I want to say something like then in this case I would look at the beam splitters looking like that. It has two input modes, A1 and A2 in. We'll have two output modes, A1 and A2 still, but this one is the out. I'm looking at the outputs as if they are Hamiltonian evolutions of the inputs. And then the problem is, as always, that, so if I'm looking at that here, so say that I'm looking at A1 at the output, that equals, well, okay, so I'll take here A1, then e to the minus I, A1, A2 dagger, plus A2, A1 dagger, times e to the I the same, now I want to calculate this. I would very much like to exchange these two and then take those two to die, one against the other, but I cannot because A1 does not commute with A1 dagger. A1 commutes with almost everything here except A1 dagger. So I can now let's see, I can calculate, but what we are lucky about is that there's a very useful theorem for that with just one yes. Well, okay. So what did I want to do now? I wanted to exchange this with that. Then there's a theorem that I don't see in my that I was sure I remember, but there's a theorem saying that something like this: e to the a times b times e to the minus a equals what? B plus commutator of a and b plus half commutator of A and B, and so on, plus 1/3 commutators of commutators of commutators. Have you seen that? Have you
Yes.
proved that?
In quantum 1.
Okay, very good.
In the שיעור הבית.
So, yeah, so we can do that. The only thing that I don't remember and I don't have written is whether it is A, B, and A again and again and again, or actually if it's the other way around, if it's B to A and then B to A and so on. We can try to see which one of them works, okay. So, but in this case, then that would be like, okay, I'm going to have A1 plus A1 dagger plus I commutator of A1 and A1 A2 dagger plus A2 A1 dagger and what else? I think that there will be nothing else because yeah, I think that that's probably the only commutator that we're going to have. And actually, yes, we almost have it. So in that case, we will have, yeah, what does it? So commutator with this one is 0, commutator with that is A2. So it's going to be A1 plus I A2. The only thing that we're missing is the 1/square root of 2. Where did that one go? I don't remember. So probably what we need is that the Hamiltonian is not this, what it is, this. And then we're fine. Because then everything will work. Okay, so that actually is good. So it's not that you can look up the Hamiltonian that represents a beam splitter, but all that I'm telling you is, look, the evolution of a wave packet through not a wave packet, a wave function or a state, quantum state, through an interferometer is simply the you can write it as there is some interaction here which is represented by a Hamiltonian of a beam splitter. Then there's another interaction which represents the propagation. This is nothing but a phase. And then there's an interaction that represents the second one, and it can be written as a Hamiltonian. So this whole thing is a Hamiltonian. So the entire flow through the interferometer is Hamiltonian evolution. And the total evolution is e to the IH beam splitter times e to the IH propagation times e to the IH beam splitter in this case. And that's what, so you can think of this as a total Hamiltonian. Now, since those actually even commute, you can, well, now that. So the question of whether you can write this as a sum or not depends on whether these Hamiltonians commute with one another. They don't necessarily. So, and that is important. So basically, when we're looking at an interferometer and analyzing it, this is like saying, okay, I had a quantum state or a quantum operator. Then time evolved. This state or operator was not an eigenstate of the evolution, and therefore it evolved. And we can calculate that. So this is what we're doing all the time. Tov. So, and now I want to go back. So that was understanding the concept of an interferometer and what do we mean by what do we mean by looking at or using that? Basically, what do we mean? What does it represent in terms of, or how to analyze this as really as the dynamical evolution of a quantum system? In a way, we could say something like, look, light comes in and then it evolves. There's an interaction in that beam splitter that is represented by a Hamiltonian, and then there's time delay, and then there's another interaction, and so on. Okay, we've said that already, so now let's do at least one calculation using this relation. So
the first method.
what?
The first method.
Well, as I said, we can use any one, but yes, let's use the first method and just calculate what will be now. Okay, so I'm going to calculate, so I'm going to take this state in this case, and I want to calculate first the average number after the beam splitter. Okay, so I want to calculate the average and uncertainty of what happens immediately after the beam splitter, and then what happens here, the output. Okay. So what we're going to do now.
So the output.
I'll explain again. Can I erase this? So Okay, I want to calculate the variance of the variance and the average. So I'll calculate like n1 average, which is equal to and that, which is basically so. Okay, let's do that. So I want to calculate that. So I'll say something like, look, I have here n in mode 1 and n in mode 2, and here I'll have, okay, a1 dagger cosine phi plus I minus I, a2 a2 dagger sine phi times a1 cosine phi plus I, a2 sine phi, multiplying n and n. And now, okay, so the only terms that will do anything is what takes a1 dagger with a1 here. So I'm going to have, so what is important out of all this is only a1 dagger a1 times cosine squared phi plus a2 dagger a2 sine squared phi. The mixed terms will not do anything. Now, and of course you can see that both of them will yield n, because we just count their own mode. So I'll have here n times cosine squared phi plus sine squared phi. So that is n for any phase. The output intensity, the average number output, is just the average input, no matter what the phase. So that is independent of phase. That's surprising. Well, maybe not surprising. The input is such that I input the same intensity in both inputs. So I can mix them any way I want. But if the inputs are the same, then the outputs are going to be the same. But that's an interesting fact. And now I can do the same, but now I'll ask myself what is, so now I need to look at this squared. So let's just, in order to get that squared, let's do a little bit of massage onto what is written here. So I need to get b1 dagger b1 squared. I want to write what that is. So before I'll write it up here. So b1 dagger b1 squared. Well, that is a1 dagger cosine phi plus I a2 dagger minus I a2 dagger sine phi, and then multiplied by a1 cosine phi plus I a2 sine phi, but then I multiply again by the same thing. And I'm careful not to write, to just square this, because that's not the same. Now, or you know what, before, actually I want to, let's make that simpler a little bit. Before I write that, there is a simpler way to do this, I'm sorry. Oh, sticks, good. I can write it b1 dagger b1, b1 dagger b1 let's first make it normal order. I don't like this one, so I commute them. So that equals B1 dagger squared times B1 squared. What? Plus or minus? You tell me. I think it's plus. Do you agree with this? You understand what I did?
In theory.
What?
In
No,
theory.
no, no. In practice, do you understand what I did? What?
In the commute relation.
I commuted this. I said that this equals B1 dagger B1 plus 1.
Now, yeah.
No. So that. Let's make sure that I'm correct. I think I am. Now, okay. So here, now I want, okay, so that's written, and now that is more convenient. So now I can calculate, I want to calculate this. So I'm here. So let's express exactly what did I want to calculate. So I wanted to calculate this. So we wanted something like B1 we have, so here we have this average is simple, right? So now I want to ask myself what this is. Okay. So I want to calculate the average of, we're asking ourselves what is the average of B1 dagger B1 squared. What is that? Well, we've just figured it out. This is B1 dagger squared, B1 squared, and then plus B1 dagger B1. Now, this one, I know what it is, it's n. I have to calculate only this one. That's actually going to be, this is going to be rather simple, because this is going to be like the average of A1 dagger cosine phi plus minus I A2 dagger sine phi squared, A1 cosine phi plus I A2 sine phi squared. And then I want to calculate the average of this. And then here there's going to be plus just n, same that we calculated before. Now here, again, what do I care about? I'll have here all kinds of, let's see, what, I'm only interested in situations where I will have A1 dagger and the same number of A1s on the other side. So which are the interesting cases? We have, okay, A1 dagger squared times cosine squared phi, and here A1 squared times cosine squared phi. So that's one case. So A1 dagger squared times A1 squared cosine to the power 4 phi. This is one such term. of course, I'll also have this dagger. So I squared is minus 1, but it comes from here as well. So the minus will disappear. I'll have a plus. So there will be plus a2 dagger squared a2 squared times sine to the power 4 phi. But there are also terms like a1 dagger a1 times the mixing term from here, which contains a1 dagger and a2 dagger, and the mixing term from here, which contains a1 and a2. Right? So there would be another one that will contribute is the let's see, twice from here and twice from here. So that will be and I, in this case, it's going to be minus 4, I think. Yes, a1 dagger a1 times a2 dagger a2. Why am I allowed to a1 and a2 commute? Only a1 and a1 dagger, those are the only ones that don't commute. And then times what? Times cosine squared phi and sine squared phi. Are there any other contributions that could be important? I think not. And is it indeed that? I think so, yes. So that is expanding this, what is important within this multiplication. What else could be? Nothing else. That's about it. All the other mixing terms are going to die. Now, what does this give me? This gives me n times n minus 1. Do you see it? But why will it give that? Well, a1 on n will give n minus 1, and then this one will give n minus 2. And a1 dagger on the other side will do the same. And so we will have a sandwich here between n minus 2 and n minus 2, which is fine. And those will be the terms just come out. And the same goes here. This one is also n and n minus 1. And this one will give n and n as well. So this will be n squared. So what will we have here?
I think it's supposed to be in plus.
What? Here? This is going to be a plus?
Minus 2i times 2i.
Minus 2i times plus 2i. You're right. It's going to be a plus. Accept. So we have here, what is this? Is n times n minus 1 times cosine to the 4th of phi plus sine to the 4th of phi. Let's see, plus 4 times n squared times what? Times, well, I can actually write it. Now you can see 4 times cosine squared times sine squared is sine 2 phi to the power 4. Okay, plus n times sine 2 phi, not to the power 4, square root. And then there's this n that we had before. So I'll write it just like that. Plus 1. This plus 1 is because of the plus n that we had here. And now I can calculate overall and to say that the uncertainty
But it's supposed to be n squared.
annoyingly correct. No, so if, but wait, as this one is n squared, then not plus 1, sorry. If this is n squared, then here we will have, this is plus n. Now the question is, what do we, so the uncertainty squared of b1 dagger b1, that is, well, okay, actually, you know what, I can, no, sorry, I can make that a little bit nicer, okay? So, sorry, I'm writing this a little bit nicer. Okay, we have, so we have n squared from here. N squared times cosine to the power 4 plus sine to the power 4 plus, let's see, I'm going to take only twice from here, sine squared times cosine squared. I'm writing it like that. And then, why did I do this? Because,
It's one.
yes, this is 1. And then what else do I have? So I have here n times, okay, so I'll have here plus twice n squared sine squared cosine squared, and then this is from the 4 that was here before. Oh, I'm going a little bit, and then now let's see, what did I miss? I forgot the n minus 1, so there's going to be minus n times cosine to the power 4 plus sine to the power 4, and then but there's a plus here, so there is going to be like minus 1. So what did we have eventually? So overall, what is this? It's going to be n squared times 1 plus this 2n squared. Sorry, so I'll put here a half n squared sine squared 2 phi. This is from here.
You can do the same to the minus.
What?
You can do the same to the minus.
How? No, but this is not 1. Here I have a minus 1, so I need to, I mean, I can add and subtract this again and do the same. Okay. So, yes, I can say that, well, you calculate this for me. I don't, that's the point, that's not the point. The main point is that I need to calculate this, and then we have, so we have this one, and then minus n times the sublime, and the point is that then I need to take minus. So that was I wanted to calculate this, so I need to subtract that. This is n squared. So eventually I'll have here minus n squared because of this, which is n squared, and this guy dies, and we have that so I agree something like what is
The same, it will be 2 sine squared cosine squared.
there's a minus sign here as well.
In the brackets it's positive.
What?
In the brackets I think positive.
Okay. And I can say that this equals, like, let's cosine to the power 4 plus sine power 4 plus 2 sine squared cosine squared minus 2 sine squared cosine squared. This is 1. So, and the 1 with the minus 1 goes, and we're left with this with a minus sign, but there's a minus here, so it will be a plus. So eventually we have here, okay, plus half n times sine squared 2 phi. So, okay, good. Now we have a nice conclusion. So the uncertainty shows the following. It is half n times n plus 1 yes times sine squared 2 phi. Now let's look at this. So first of all, this interferometer shows a surprising thing. Okay, so what is so surprising? First, the average number of photons is independent. So B1 dagger B1, the average number of photons is n no matter what. So usually we say, look, I'm going to measure the intensity and see the difference. There's no difference. There's no phase relation. No matter what you do, the average number of photons is going to be the same. But there is something that is dependent on the phase, and that is the noise. Specifically, when the phase is 0, there's no noise at all. When the sign is 0, then this means that if I want to now look at this interferometer, and I can so yeah, I mean, in this case, if this is the phase, then I don't know, if I look at B1 at like N1 or 2 at the output, doesn't matter which, this is just constant. This is equals N in. It doesn't change. So if I look at that, but if I look at the uncertainty of that, so if I look at the uncertainty, then that does this. It goes like sine squared of 2 phi. It goes from 0 to about n and back. And this is at pi over 4 pi. That is the uncertainty of n, 1 or 2 out. Now, it's not exactly, well, you see, it's even higher, it's even more than n. So, first, if I could measure, so now I can decide that I want to extract a phase. And then if I could measure the noise, I'll be extremely good in doing that.
But how you measure it?
What?
How you measure that?
Well, the point is, and why is that so good, that doing this, and that is because, sorry, I should be, this is,
It comes up to half n squared plus half n.
no, but there's a sign. Yeah,
but sine is 1.
Okay, so you're telling me, look, I'm looking at the square root of that, and
For large n.
yes, and for a large n, then this is like 1 over square root of 2. But you're right that I should be careful. Now, okay, but there is what I did want to say, and that is that when I take, if I look at now that is the variance. So the variance goes like the sine squared. So the standard deviation. So we'd have here like delta. This just the delta itself. This one goes like n times sine phi, sine 2 phi, absolute value, right? So if and that's actually good. So for small phases, so if the phase is small, so what did we have here? We had something like half, 1 over square root of 2 of that. So for small phases, this is a function of phi. For small phases, now there are I could write here like square root of 2, but now this is a scaling. I'm not sure about the prefactor here, but what is important is that this scales linearly with the phase. So I could say something like, okay, when is, assuming, what is something that I can measure? If I could measure that noise, so what will I be? Okay, so when the phase is 0, then the noise is 0. And then what will be a noise that I can measure? Maybe on the noise on the order of 1. So if I'll do a measurement, and I will see that sometimes I'll do 2 or 3 measurements, okay? And I'll see that sometimes I always get on average n. But when I sit exactly at phase 0, it is always perfectly n. So I'll do 3 consecutive measurements, and I'll see always n, n, n. And then I change the phase a little bit. And then again I do 3 consecutive measurements. I don't know what I'll get. On average it's going to be n. But there is a chance, I don't know, about 50% or maybe more, that one of them will be maybe n plus 1 and the other one will be n minus 1. Because it's a small phase. And n plus 1 and n minus 1, if I can count photons exactly, then I'll be able to see that. Okay? So the minimum phase that I can see, is when this is equals 1. This is what is the requirement for a minimal. And then, and that is something like 1 over n. Now if it's 1 over n or square root of 2n, it doesn't really matter. Now this is a great scaling. This is called, this is the Heisenberg. This is called the Heisenberg limit. And that's actually the best you can do in quantum mechanics.
Can you explain again why you want?
Because I'm saying something like, look, I'm telling you that in this crazy state that I cooked up, just measuring the average number of photons will not help you at all. The average number of photons is always the same.
Minimum differences must be 1.
Yes. But I'm saying that, but what does change? What changes is the noise. That means that when I'm exactly at phase 0, there's no noise, ever. So it's always n, n, n. Okay, so let's say, okay, I'll do 3 measurements. I'll be quick. Okay? So I'll run the experiment 3 times, and I got 3 times n. So most likely there is, it's probably that the phase is very small. Maybe if I'll make 1,000,000 measurements, I'll be able to tell that there's a small phase. But let's assume that all I'm doing is 1 or 2 measurements. Okay? So if I made 2 shots and I got exactly the same number, I say, okay, there's no phase. And then I make 2 shots and I get different numbers. And then the question is, will it be reasonable to assume that I will get a different number? How much phase do I need for this output to change from shot to shot? And the answer is, well, if when the standard deviation is going to be 1, then you can expect the average plus minus the standard deviation. So if the standard deviation is so the question is, what is the phase that will make a standard deviation of 1? And indeed, so that's actually very good. Why? I don't know if you remember, I think what we calculated the Mach Zehnder with the coherent input. Because the classical limit, so, okay, let's see. That's the Heisenberg limit. Classical limit is what happens when we have the state to be a coherent state in mode 1 and vacuum in mode 2. That's what we can do classically, and then we will get a different behavior. We need to do the same calculation, but now I want you to believe me that in this case, the minimum phase is 1 over square root of n. Now, if n is large, where n is the average, so
Why not square root?
What? What?
Why not square root on the alpha?
Well, because n is alpha squared. So, and you can see that this is definitely better than that. Okay, so now we understand. Now, I think, I don't remember, did I show you or did Sar show you this? I think we did, but good. Then, and this is called the shot noise limit. Now, so you can see that we can hope that a quantum, a non-classical state can lead to a dramatic improvement in the sensitivity. There is a but. The question is, can you prepare that state and can you measure what needs to be measured? What I just showed you was a completely stupid example. It works on paper. If I could make exactly equal number of photons entering here and here, if I could make that, then, and if I could measure the noise perfectly, do a really good measurement of the noise, meaning that I really need to exactly count how many photons are in port, whichever port I look at. I can look in both of them also. If I could do that, then great. Then I'll have a measurement that is much, much better. But how do you make this state? How do you make a large N exactly the same in both ports? And then and the answer is, well, that's somewhere between extremely hard to impossible. Maybe I can do that with numbers like 2 or 4 photons. But 2 and 4 are not very big numbers. So that will be an interesting demonstration for a scientific kind of thinking. But if you really want to measure a phase, then, okay, indeed, classical physics tells you that you're limited by 1 over square root of n. But classically, n can be very large. We can increase the power as much as we want, and then the average number of photons will be as large as you would like. So now we want to talk about states that actually allow us to go that way, to see an improvement, and maybe even, and the question is, can we even go towards the Heisenberg limit? The answer is, in theory, yes. In reality, forget it. But we can definitely improve. So we can. So what about states that we can actually make, and that will be useful for this? We can. So okay. Tell them that they need to. They need to get back or something.
Yeah, I told them.
So we started talking about squeezed states and squeezing, and I told you that okay. there's one more thing that I want to identify. And that is that so now I'm going to talk about, first I'll talk about squeezed vacuum. I'm going to talk about, generally we're learning about squeezed states, and specifically we're going to discuss a squeezed vacuum and squeezed coherent state. Now, what does it mean? Squeezed vacuum means that I take vacuum and introduce it through a squeezer. Now, we discussed what a squeezer is last time. We talked about the parametric amplifier. Okay, so we talked about the squeezing is equal to parametric amplification. And parametric amplifier does what? If I think of an operator A is equal as being some x plus iy, or p, well, you know, and those are now, I can put hats on that, but I don't need that. Or in other words, I can say that x equals a plus a dagger. Usually we do it like that, and y equals 1 over 2i, a minus a dagger. Under this assumption, then a parametric amplifier transforms this into, so if a in equals that, then a out is x, that was the input. What the parametric amplifier does, it amplifies one quadrature and de-amplifies the other. So let's assume that this is x. So let's say that it does this, x times e to the g plus I y e to the minus g. Now it's not the same parametric amplifier, and if I take that and put that one here and this one here, then we will get that this the output equals hyperbolic cosine g times a plus hyperbolic a dagger as hyperbolic sine g. Now, the other thing, so this is, we'll talk about that in a moment, this is the squeezer transformation. Look, and it is similar to what I told you about the beam splitter, if you remember. With the beam splitter, okay, there are all kinds of, in a moment it will be even more similar to what we had about the beam splitter. But so that is the relation between the input and the output. I want to be even more specific. I want to explain why that is also a Hamiltonian dynamics. I can also explain that this is and that is, this has a Hamiltonian. This Hamiltonian is G times A squared Sometimes it has an I here, but that plus a dagger squared. It's not the same Hamiltonian as we had for the beam splitter. It's a different one, of course. But the parametric amplifier has a Hamiltonian associated with it. That is let's call it. So I want to show you that first, okay? So I would like to show you that indeed, if this is the Hamiltonian, then under this Hamiltonian, then I can say something like, okay, A out equals A in times e to the I h parametric amplifier e to the minus I h parametric amplifier. So I can write that as being, let's do it. So e to the, usually people write here I, have the I here, and put here a minus, and you will, now in term, it doesn't really make any difference. This is a Hermitian operator, and the reason I do it, because usually we like to write the propagation in time as e to the I something, and then what will happen is it will just dictate which quadrature is going to be stretched and which quadrature. With this I and this definition, I will get to this equation. And if I didn't have here the I, those two, I would get the dagger right. It would behave. I think then we would get here a minus sign, and then it will be amplifying the other quadrature. Like instead of amplifying x and de-amplifying y, it will be the other way around. But so that part is not, whether I write here this or I write here this, this is not going to make a difference. You can actually check. Okay, so this is, the I disappears, so I will have here minus g a squared minus a dagger squared times a times e to the g a squared minus a dagger squared. And as we said, this will be a plus a times, sorry, the commutator of a and g a dagger squared, and then plus half the commutator of a with the commutator of a and g a dagger squared. Why do I go only for g a dagger squared? Because this is the only thing that it doesn't commute with. Plus 1 over a and so on. So now let's first calculate this. Now this is simple. Okay. So this will be, what is that? That will be 2 times 2, yes, 2g a dagger. Do you agree? Because the commutator between a and a dagger squared is a dagger itself. And I guess you calculated commutators like that. You're constantly silent, so I need an approval that you know why this is what I got, or you. So now, so here, I'll have. So this commutator is just the dagger, and then the commutator of A with the commutator. Now I'm. No, I got something. I think I got something wrong. Wait. Let's see. Oh yeah. Something is going wrong here. This is true, but
What is a square?
what?
A square.
No, the a squared is not a problem. There is only because we commute with the a squared. What we don't commute with is only the a dagger squared. But what I probably should be doing is, I think, yes, okay, sorry. I got the formula wrong, I think, and therefore should. The commutator of this with that, so this would be the commutator of, there's going to be a minus sign, and then G a dagger squared with A. And then here is going to be G a dagger squared with G a dagger squared with A. And it will be a plus because and then here again a minus, and then again G a dagger squared with the commutator. Now this commutator is indeed 2G a dagger. And then what? Then we will commute, and then I should be careful because then I'll have here, I'll be commuting, oh, I should be careful here. So here I need to write the full equation. There's going to be G times a squared minus a dagger squared. Have to write this whole thing. Why? Because then the point is that this commutator we just calculated, it is 2G a dagger, and then when I commute it with this one, I'll have here then this a squared will need to commute with this one, and then I'll have here 4 times G squared times A. Why? Because we're commuting now. what doesn't commute is the a squared with the a dagger here. And then what will be here? We can calculate. This is going to be 2 to the 3, g to the 3, a dagger. And the sign is flipping. So eventually what we will have is a minus 2g a dagger plus 4g squared a minus, half. Half times, let's write it like this, 2g squared a minus 1 over 3 atzeret times 2g to the third power a dagger, and then plus, and so on. And now this looks almost like an exponent, but now we need to collect all those and all those. And you can see that what we will have from the first one is the hyperbolic cosine. So that would be a times hyperbolic cosine. Now I think that's going to be actually the hyperbolic cosine of 2g, not g, but this only has to do with whether I should have written here a half. Okay, so so forget about the half. With this, we have hyperbolic cosine of 2g, and then what we got now is minus a dagger hyperbolic sine. Almost what we planned for. Now maybe I think that but I calculated the commutators wrong, because in this case we will also get a minus sign. In one of them we will always get a minus sign. So instead of, I think that this actually makes all of those be a plus, but and then this becomes a plus as well. But forgive me. I'll tell you, I am correct, but I'm not. I don't remember which of them I need to flip. I'm telling you that this one becomes a minus, and this one becomes a minus. Now, why am I saying that? Because this commutes a dagger with a. So the other one commutes a with a dagger. So we remember that the commutator of a and a dagger, that is 1. So a dagger in a, I'm sorry about all those signs, but this is. So then that is what happens. So in the Heisenberg picture, I can say that if I have a device with this Hamiltonian, then this device will transform the input operator. So when I go through it, I will transform the input operator to something like this. And as I just showed you, this relates to amplifying one quadrature and de-amplifying the other. And therefore, this is, at least we can just see why we call that squeezing. Because, for example, it will take the vacuum. So if I think in the xy plane and I say that the vacuum is something like that, then it will transform it into, in this case, I don't know, something like that. It will squeeze it in one dimension and amplify it in, or so it will squeeze it in one quadrature and amplify it in the other quadrature. So now, I told you what is the Hamiltonian of the parametric amplifier. Now, let's say, oops, what is it? It is related to either disappearance, annihilation, absorption, conversion of two photons, or emission, creation of two photons. This has to do with processes where pairs of photons are either generated or annihilated. So now I want to tell you about such a case. So how can we really, the point is that it is very easy to make this Hamiltonian, at least to an extremely good approximation. Okay, so first, what does this Hamiltonian do? It squeezes. This is the operation that it does. It amplifies one quadrature component and de-amplifies the other. It transforms the operators according to this equation, which we just showed. And what I want to show you also is that this is extremely easy to make this. And what is the process that does that? So I'll remove that for a moment, if you will, and then I'll so I want to say that this Hamiltonian is not very common, but the question is, there are situations where an atom or many atoms in a crystal can now I'm showing you some kind of a Feynman diagram, and I think that many of you may have seen that. What does this represent? This is what I did right now, is I drew a Hamiltonian. What is that Hamiltonian? This is the Hamiltonian that says kill a photon. A photon in the pump in omega 0 was disappeared. So let's call that mode pump. Okay, so this A pump is one photon was killed, and then two photons were created, where in this case at exactly half that frequency. So this process that I drew is this. I don't know, let's call that, if this is mode, I don't know, 1, sorry, let's call that mode 2. This is omega, and this is omega over half, and this is mode 2, which is the pump, and this is mode 1. So this is A2, A1, dagger squared. The point is that if you can annihilate one photon from here and generate two here, you could also do the opposite. So you must have also plus A2 dagger, A1 squared. That is a Hermitian operator. There will be some coefficient, and that is the Hamiltonian of that process. This is the Hamiltonian of what we call three-wave mixing, or in this case, degenerate three-wave mixing. Now, I must say, so this is in this case, this is also degenerate. Now, why is that? Why is this and this the same? the point is that the pump, the A2, assuming usually this pump is very strong. And you already know that if for a strong pump, I can replace that as being as alpha pump. And I can replace this as being alpha pump star. And this is true for strong pump, strong coherent What do I mean? I mean that actually the state is, so when I say I have a state at the input, I can say that, look, this is alpha, which is very large, on the mode 2, and I don't know, some unknown psi in mode 1. I don't care what that one is. Now, the point is that this operator will operate on that. And here, to say that I'm operating with A will definitely get alpha out. And when I operate with A dagger, I won't really get alpha pump star, but I'll get extremely close. So that's why, and then this is called the approximation of a classical pump. So if for a strong coherent pump, I can assume it to be classical, and therefore neglect any quantum properties of that pump itself. And then this becomes that. You can see why. Okay, so for a strong pump, this Hamiltonian of three-wave mixing becomes approximately this, like chi alpha pump A squared, A dagger squared, plus chi alpha pump star times A squared. And then you can see that I can call this one G, and assuming that if the phase is 0, then this will be a plus, and if the phase is pi, then this will be a minus. But in any case, we'll have here like for alpha pump real, and then it depends if it is positive. If the alpha pump is real, then what we have here is like this equals G times A squared plus A dagger squared. If it's imaginary, then there will be an I, and so on. You got it. So actually, first, it is very, and now I want to say something about three-wave mixing in general. Okay. So, and three-wave mixing, that is actually something that, I told you a little bit about, so that is the Hamiltonian of three-wave mixing, but now I'm going to do bad service to nonlinear optics. So I really do want that you would go and learn nonlinear optics, classical nonlinear optics. Because this process is very common in nonlinear optics. Meaning, for example, specifically the inverse process of going the other way around. Like, I mean, if I go from here up and then here down. This is called second harmonic generation. It is, and it will normally happen. And let's say when does it happen? So like I introduce frequency omega into a medium and I get out frequency omega time doubled omega. When does this happen? Very easy. If I need a medium. So very quick nonlinear optics. You know that the dipole, what you learned is that the dipole in a medium is proportional to the field. In general. And then, and really, well, that is of course correct, but let me remind you, what is the dipole? If I have a field, and I have an atom composed of electrons and composed of positive and negative charges. Now I have a field, so I'm coming with a vibrating field. So I'm going to shake them. And I'm going to shake them in opposite ways. So I'm going to induce a dipole inside. So they will be like, initially there's no dipole, they're like the electrons are close, and then we pull the electrons up and the protons or the nucleus down, and we're doing it like this. So we are inducing a dipole in the medium, and this dipole, then it's a vibrating dipole, so it will emit light. It will emit light in the same frequency as we modulate it in, and it will, and that will interfere. But so this emitted light has a phase to it, and then things depend, and this is where the absorption comes from, or stimulated emission comes from, or the index of refraction comes from, always from this linear response. And the question how this dipole, when it emits, interferes with the field itself. The point is that the assumption that the dipole, which is the response of the atom to the field, is linear in the field is just a first order approximation. There are, so this would be chi1, and there is chi2, e squared, and chi3, e cubed, and so on. Now, let's see. So how would the dipole behave? So if E equals, I don't know, A times cosine omega 1t. Let's assume that. Then what will the dipole be? So P would be like P1 plus P2 plus so on. I'm going to look at the contribution of P2. So, well, P1 is just simply chi times A times cosine omega 1. So now here there's little difference. But here we will have chi1. And then here we'll have P2 will be chi2 A squared times cosine squared omega t. And cosine squared omega t is half plus half cosine of 2 omega t. So here, when you square, you generate new frequencies. Which frequencies in this case? DC, and this is the double frequency. So if you have a medium with a nonlinear chi2 response, it will generate a square. And I just told you, okay, so this generation of the square is no surprise classically. The fact that it happens is fine. And it will it will so this, the fact that you can have the double frequency is exactly due to the fact that you square the field. But squaring the field is, and squaring the creation or annihilation operator, those are the same, if you remember. Because the classical field transforms into the creation and annihilation operator. So, really, this Hamiltonian is simply the Hamiltonian of a medium that can that has a nonlinear response which can do a square root, a square, and this represents up conversion, meaning killing two low frequency photons and generating one at the higher frequency, so generating the double frequency. Whereas this represents the opposite. Kill one high frequency photon and generate a pair of low frequency photons. And how does this come about? By having a nonlinear crystal with a nonlinear response. And then the process inside, as we said, is like we temporarily generate a dipole that oscillates at twice the frequency because it contains the square component. And then this dipole emits, and so therefore it emits the double frequency. And that means that into this crystal we get in with infrared light and we get out green light. Or I don't know, you come in with red, you get UV. So, and that can go in the forward direction, I don't know, depending on what you call forward and backwards. But we can go from infrared to green, and that would be frequency doubling. But we can go from green to infrared, and that would be down conversion. That would be pair emission, and this is exactly what we need for this process to happen. So a process that can do this, so that means that I can easily make, so this is a Hamiltonian that I can make, and what's good about this Hamiltonian is that this is a squeezing Hamiltonian. So what it generates is squeezing. What this Hamiltonian of the parametric amplifier, which is simple to have, what it does is it does this operation, it squeezes. Now within this map, it's simple to think about, well, as I told you, this is what it does to the vacuum, and I can think about, say, a coherent state. So this is a coherent state with a coherent amplitude alpha. This is the vacuum shifted by alpha. That's all that it is. And then what will happen? So I can say, well, if this is x and this is y, then what will happen is that x will become stretched. So here I'll have, say, e to the g times x, and here I'll have e to the minus g times y. So this one got stretched by, say, 2, this one got So the average amplitude is going to experience this, but also the uncertainty experienced that. So that means that I will have here an uncertainty ellipse. It's going to be an ellipse. So if this is vacuum, this is vacuum and this is squeezed vacuum, and this is a coherent state alpha, and this is a coherent state alpha squeezed by G. Now actually it's not exactly the same alpha. Let's call it alpha prime, because you see the coherent amplitude itself also changed. So if I take a coherent state, any coherent state, and the vacuum is also a coherent state, I will generate a squeezed coherent state. And coherent states are simple to make. That's what a laser makes. And therefore squeezed coherent states of any kind, vacuum or none, is simple to make. Now, okay, so I'll say something rather quick. So all I'm saying now is something that, look at it. So therefore things are going to be very similar to what happened before with the beam splitter. So I have an input operator. I have here a state, say vacuum. And then here I have an output operator, and say this is psi in. And I can say that I have here psi out. I don't know what it is. Now I can, for example, look at, say, look, I'll have A out. That now I know what that is. I just showed you. So this is A times hyperbolic cosine of G plus A dagger hyperbolic sine of G. Now I can, so I don't need to, I don't want to know what psi out is. Now I can say, ask, okay, so tell me, for example, what is y squared average at the output? What is that? Well, that's easy. What it means is that I want to calculate the average of A output minus A dagger output. There's a half and I, but let's forget about that. And I'm going to have that squared.
It's I, right?
What?
I, not Y.
What do you mean?
The intensity out.
No, I want to look at the Y at the output. Not intensity. I didn't mean, no, not phi and not I, but Y. Okay, so I'll be calculating. I want to calculate this. Well, okay. But the point is that now this is simple, because this, I know what that is. This is e to the minus g times y that was at the input. I can, I can just put the equations that we had before. I mean, I can use this and calculate that, but you know that this is what was there. So this is going to be e to the minus 2g times what? Times, times psi in y in squared psi in. Now if that was vacuum, then this thing is half or quarter or 1. It doesn't matter. It's whatever vacuum does. This is the vacuum result. So we have e to the minus g minus vacuum. So this, no surprise, is e to the minus 2g times vacuum result. So times y squared average of vacuum. So therefore it is squeezed, and if I'll do the same for the stretched quadrature, it will become stretched. And why? And now very briefly, why is that good? So I think we learned how to measure. So squeezed vacuum indeed shows that if I measure the variance of one of the quadratures, it's going to be small. Now I want to make a very quick connection to what we had before. So first, connection to phase measurement. So one, homodyne measures quadratures. And two, this is very, so what is homodyne? This is just a beam splitter, and here I'll send a state alpha for a local oscillator, and here I'll have a state psi, whatever it is, and then here I'll have two measurements and take the difference. And this we already know, and we know that the difference of this gives out absolute value of alpha times x or y of the input. We have seen that before. Now, but what is an interferometer? So if I would send here this state that I call 0G, which is the squeezed vacuum, I'll measure that. I'll be able to measure the average of y, and the noise will be small. I'll measure exactly this. And the other thing that is important is that an interferometer is equal to homodyne. An interferometer is equal to homodyne for a specific case. For phase near, for phase near pi over, well, it depends on what we write. I think that in the way I wrote it is pi over 4. What do I mean? I'll remind you that B2, B1 equals what? Cosine phi, sine phi, minus sine phi, cosine phi, times A1, B1. When the phase equals pi over 4, so this is like a 50-50 beam splitter. So the entire thing so if I have here, I have a total interferometer, and I have here, say, a coherent state alpha, and from here I'll introduce squeezed vacuum. If I can seed the unused port with squeezed vacuum, then I will see, and if here I'll measure those two intensities, and I'll take their difference, then this around near that phase, in the vicinity of this phase, will measure the squeezed quadrature. That's what it measures. It tells you what the squeezed quadrature is. And now the squeezed quadrature has low noise. If it has low noise, that's good. Now we didn't talk about sensitivity enough. But I think that when Sar will be here, he will tell you about sensitivity. And now I need to let you breathe. And let me breathe also. So we can stop here. And next week we'll close that and start talking about Bell states and entanglement, and which is related strongly to squeezing, as you will see. Yes, we will. So, questions? No, everything is totally understood.
No, still digesting.
Huh?
Still digesting it.
I prefer the okay. So I hope enjoy your food.
Thank you. So, last tutorial we talked a very little bit about squeezed light. What is it? What does it mean? I'm gonna do a quick refresher, and then we're gonna see probably one example of how to use it. I'm not sure I'm gonna do the second example. And then if you really want to, we can talk about the group theory, why we call the Mach-Zehnder SU2 and the two OPAs in interferometer that Avi apparently didn't manage to get to, why we call it SE11.
No, he didn't get to the SE11. This is the tutorial 9.
Maybe.
Let's take the mundane detection.
No. I didn't upload it. Yes.
Listen.
Okay. So, yeah. So we defined, Ravi also probably showed you the Hamiltonian of a nonlinear, of a general nonlinear crystal, usually divided by 2G. Maybe plus, right? This will give us the unitary transformation S, G, E, I, W, A. And we'll show you the transformation, you prove the transformation S dagger equal dagger. Technically, there's also supposed to be a phase component here. We'll ignore it for now. Really sure you show this transformation in your
Without the phase.
There is also a phase. Okay. This phase
It showed us that transformation without the phase.
Yeah, usually when you think about everything is perfectly clean, you will remove the phase and just say we're squeezing the correct quadrature. But technically, how these kind of processes work is that you have a nonlinear crystal, non-linear, let's call it non-linear, and then there is some pump, makes this entire operation work. And then you push in something we call idler signal, or they can be just one frequency, and then this amplifies it, or de-amplify it. And this amplification of de-amplification is based on the phase between the pearls and the pump. Yeah, I don't want to go too deep into it this tutorial. I don't know if Avi will really be happy that I expand so much. But technically this process that you saw with the one operator can also be explained in a broad sense. You know what, I'm gonna say it anyways, because it will lead and you're getting punished. You're getting punished with more knowledge.
Oh no.
Oh no. Yeah, so for example, one process that can create this squeeze state is two-level process where we have a pump to generate that excite our atom, and then our atom is spontaneously or stimulated get moved from the excited back to the ground state in 2 bits. Let's use again blue and green, which basically mean that it takes 1 photon in and then generate 2 out when it reduces back to the ground state. How much do I want to go into this? How much of a hole did I dive myself into? Yeah. And this will create. You know what? I can forget about it. I just forget about it. I'm gonna go back to the prepared material, and we'll go back to 2 mode squeezing later on in the course. Just so you know, this process is not necessarily just 1 mode. Anyway, we saw about squeezing. But if we put it on the table. I do not accept the bribes. Thank you. So anyways, we saw that if we look in the phase space, if you don't remember this stuff, we have time today, I can go over and prove it. But we saw that in phase space, if we start with the equivariant state, for example, this one, then the squeeze state, what it will do, it will keep the equivariant state, which is a minimum uncertainty state. It will keep it in a minimum uncertainty state, but it will just shift the uncertainty from one axis to the other. For example, it will change the circle into an ellipse. And then this can be very useful for us in measurement because we can measure along the squeeze axis, the axis that has less noise in it, to get more coherent result. I don't know if you remember, but last tutorial we talked about beam splitters that if we put some input field here and then some local oscillator with the same frequency, we can interfere both of them, measure the 2 outputs, and take the difference between them, and that will be us directly detecting one of the quadratures here. If you want, I can try it again, but we saw it in, I think, 2 tutorials. Before 2 tutorials, we saw that this configuration will directly give us the input quadrature, one of them. So we can physically measure a quadrature in any angle that we want, depending on the angle between the local oscillator and the input. And like that, can use the squeezing to our benefit to improve the noise. Why do I care about improving the noise? You might say, oh, it's very clear, it's very obvious, less noise at the results. But let's try to put some number on it. There are, that was nice. There are usually 2 different ways to basically quantify how good our results are, or how good our system is. There is a qualitative measurement, which is called the SNR, which is equal the measurement divided by the measurement noise, signal to noise ratio. Not very complicated. And why do I call it qualitative instead of quantitative? Because the SNR doesn't give us any physical value of the system. It doesn't give us direct information. You want it to be as large as possible, and that will mean that your system is good, that you can see a lot of signal and not a lot of noise. But there's also a quantitative measurement, which is sensitivity. Basically, I want to know if I can distinguish between two measurements. I have a system, some black box, there's some input and some output, and I take a measurement N1, and then also take the measurement N2, two different measurements, two different time, and I want to know if they're actually measurement in different config, if something changed in the system. This can be quantitatively defined by noticing that we can differentiate between these two measurements if the difference between them is larger or equal to the noise that we have in the system. If it's smaller than the noise, it could just be, I don't know, someone walked near our system and moved something a little bit. If it's bigger, then definitely something happened. All right? So let's try to do it with no arbitrary units 1 and 2, just with a physical change. Let's say we have a measurement at some phase in the system. We have some phase component, measurement in one phase, and then a measurement in phase, and then with a little bit of a shift, right? Now I can multiply and divide by the shift, n of phi minus n of phi minus delta phi. Bigger n, right? This is basically this is just a partial derivative by phi. So delta phi will be bigger or equal to delta n divided by derivative of n by phi. Usually we also like to put absolute value here. Doesn't really matter. Let's work more convenient like that. And we see that the minimum change that we can detect just when this greater or equal becomes an equal sign. This is what we define as sensitivity. It doesn't have to be with phase specifically. It could be with whatever whatever change that you introduce in your system. But this is a quantitative measurement of the quality of the system. It actually has a physical meaning. Okay. So now we can see both in the SNR and in the sensitivity that if we can just reduce the noise without increasing the intensity, which is a big asterisk, which we'll talk about later. If we just reduce the noise, the sensitivity becomes lower, so we can measure smaller changes, and the SNR becomes bigger. So it basically qualitatively means that our system is better to reduce noise. We can see it in both of these metrics. You can choose whichever metrics you like. I heard that engineers like SNR more. I prefer sensitivity. You do you. And now we're gonna do like. What do I mean by that? I'm gonna show you how we can use squeeze state to improve a Mach-Zehnder interferometer. LIGO is basically just. LIGO is basically a big linear interferometer, a Mach-Zehnder configuration. So, last tutorial we talked about the Mach-Zehnders. So we have two beam splitter, two mirrors. Then we have some measuring configuration at the end. And usually people put vacuum here on this board. If you want, I can show you the results from last tutorial when we did the Mach Zehnder, but I'll just remind you very quickly that we saw that the noise component that really holds back this Mach Zehnder interferometer sensitivity comes from the vacuum input here. Vacuum input generate fluctuation, generate noise. Forgot to draw the phase component. So I suggest that we replace the vacuum input with squeeze light and then measure in the squeeze pilot shoot. What do I mean by that? Basically, I want to take this vacuum fluctuation and reduce as much as possible, by that improve the noise. So, last tutorial, we saw that the output, I'm gonna say A goes to the A of the input will just be A plus alpha, which we saw is the operator of the coherent state, A plus alpha. Or if you want Schrodinger representation, alpha. But we'll use a combination of them both. And in the vacuum port, instead of basic vacuum, we'll use S dagger equals to be push G plus V dagger G without the fixed inside. Since we don't do interference with the squeeze state, we don't need the phase U. You can just say we squeeze in the correct quadrature. Or usually you will represent the squeeze state with an S if you want to walk a Schrodinger representation. Okay, and we saw that the output here, based on input of A out as a function of A in, was equal to 1/2 A in e to the I phi minus 1 plus I b in e to the I phi plus 1 b out b equal to 1/2 b in 1 minus e to the I phi plus I A in e to the I phi plus 1. So 4. And now what we actually measure is A dagger A and B dagger B, so let's also write those down. And A is equal A dagger A be equal to 1/4 A dagger in A in 1 minus cosine phi plus A dagger in.
What does N mean here?
N?
Number of photons out.
Yeah. A dagger A out. Right. This equation we also saw in this tutorial, so I'm just writing it fast so we'll have it in front of us. Phi yes, plus dagger in 1 plus cosine phi and B out, and B will be equal, oh sorry, that's 1/2, not 1/4 here. This will be 1/2 B in dagger in 1 minus sine phi plus minus A in dagger B in dagger A in times phi plus A in dagger in 1 plus cosine phi. Right. And now the difference between them, take the difference between them, and A minus and B will be equal to minus A in dagger A in of cosine theta minus I A dagger in plus B in dagger in sin phi plus B dagger in B in cos phi. Okay. Now this we can easily calculate. First of all, these terms. Let's look at our operators when they open out. A in is equal A plus alpha, and B in equal B cosine theta G plus B dagger sinus theta G. So you won't have symmetrical terms here. That means that if you look 0A, 0B, in dagger B in 0A, 0B, the A in dagger will create a photon here, but not here, so it will fall from orthogonality. So the same with B, just with two different terms, right? So you can completely ignore the middle term, and now A dagger A of a coherent state, we know it to be absolute value alpha squared, so it will be equal to absolute value alpha squared minus cosine theta, right? And the squeeze state, I don't know if we did it. I can show it explicitly. If you want me to show it explicitly, the result of this one. No, there yes, yes. Alright, so B dagger B will be equal to, let's call this one, so B dagger cos G plus B sinh G B cos G B dagger sinh G. Of course, this is a vacuum state on the outside, so let me take my red pen. So B dagger walking on the left state will go to 0, and B walking on the right will also go to 0, and B dagger expectation value on the vacuum state is 1, so overall it will be equal to sinh square G. So we plus square cos phi, or simply cos phi for G plus alpha to value squared. Of course, the minus sign is up to which one you subtract from which output you subtract from which one. Okay. So now we need to do the noise. It should be a bit rougher. Will be fine. Right here. So the problematic term in the noise that we don't know yet is this term. Okay. And it will look like. Bye.
This is the noise?
Oh, this is one of the terms of the noise.
Oh.
Noise is this minus
The noise
the
is
square on the
there.
outside. Okay. So. Okay. So. In output term, this will be an output term. The noise will be. Second. Just wondering if I want to do the full thing. Okay. Okay. One second. So, where is it? Yes. We have minus a delta a, so b, c plus I since phi delta b delta a squared. Because this is a and b as in input terms. So we know that we need to keep a balance. Then what the fuck is going on? Beautiful. Okay. The number of a creation and annihilation operator must be symmetrical in the number of a creation operator need to be the same number of a annihilation operator. The number of b creation operator need to be the same as the number of b annihilation operator. But you need to remember that b is a squeeze state, and the squeeze state has inside of it both creation and annihilation. Where is it? Here somewhere. I don't know. Somewhere here. Here. Yes. So we can have BB and stuff like that. Okay. So if we multiply this with itself, you will note that the term A dagger A and, for example, A dagger B cannot coexist. So A dagger A will only work with itself, and we'll have one term which is A dagger A, one term, and then we'll have another term, B dagger B, B dagger B, and then the mess start to come. We have this term squared, and this term F, and then we have this term squared. B dagger B also cannot work with the mixed term for the exact same reason, because then we have three different B operators and one A operator. It will not work. So we have A dagger B, B dagger A. We have A dagger B, A dagger B. This will not work. This will work. You will see in a second why. We also have B dagger A, B dagger A, and we have B dagger A dagger B. Yes. Okay. Now let's go one by one. A dagger A dagger. This first one. This one will be equal to conjugate A plus conjugate plus alpha. Then this one A dagger plus alpha conjugate A plus alpha. Okay? First of all, we can remove the term on the outside. A operating on a cat, 0. A dagger operating on a bra is also 0. So we have, so it's equal to absolute value of alpha squared. And then we have this internal alpha, so again alpha squared. And A dagger is equal to 1 plus 1. Right? Now for the B dagger, B. Bit annoying, but let's see if I have it like that. No, I don't have it like that, but we can just, let's do it fully. And then I'll give you the it's B dagger cosh G G B cosh cosh G plus B G cosh G plus B dagger sich G. Again, this one removes, this one removes. So we have the term B dagger with sinh to the power of 4, and this will just, and B dagger, you can do it manually and set it equal to 1. So we have sinh G power of 4, and we have B dagger, B plus 2 sinh squared G cosh squared G. Right? So ugly math will do fine for now. Now for the mixed terms, so do I have it? Do I have it? I don't know. Let's do simple mixed term. This one. A dagger B, A dagger B. I told you that it works. It's not 0. But let's open it up. We got A dagger plus conjugate. We got B cosh G plus B dagger sinh G B dagger plus alpha conjugate, and then B cosh G B dagger sinh G. Right? We'll again remove the terms that we can remove. A dagger from the start we can remove. And this A dagger has no partner, so we can also remove it. Now, B dagger is also on the left. Remember, B and A, you can commute them, so it's effectively on the left. So B dagger here can be removed, and B on the right can be removed also.
Why did you remove the middle B dagger?
This one, operating on the left.
Then minus 0.
I mean 0. Yes. So we get a conjugate times B dagger, so it's 1 times the cosh.
Squared, right?
Yes, squared. Cosh G sinh G. Okay. Of course, we also see this term would just be the complex conjugate of this term. This and this are just complex conjugate. The next term, b dagger a, just equal alpha squared cos g sinh g. And I can't find, where is the last mixed term in my notebook? That's a good question. That is a good question. I can't find it. So let's do one and I'll give you the final answer. Okay. So let's do a dagger b dagger a equal to a dagger conjugate, and then b cos g plus b dagger sinh g. Yes, b dagger cos g plus b sinh g times a plus b. Yes. Right, again, I'm going to move whatever I can. This one and this one on the left, on the right. And then here again, b dagger on the left, b on the right. So we just have absolute value alpha cos g squared. And we'll get a similar result to this one, just with the plus 1 in there. Eventually, what we get is I know why my notes are a bit messy, because the way I wrote it, I already determined the phase before I started calculating everything. If we'll pick the phase that minimizes our intensity, which will be a dark fringe, it will be pi over 2. Usually we like to do measurement at pi over 2. This is what I'm going to do here. So I'm just going to take the phi here to be pi over 2 for the first part, and we'll get that NA minus NB squared for phi equal pi over 2. In my notes, I will fix them because I see I didn't fix them and I want to do it. I'll fix them and I'll put the full answer in my notes. It's a waste of time right now. This one will be equal to alpha squared of 2 sinh g cos g plus cos squared g plus sinh squared g plus sinh squared g, right? And the term NA minus NB squared and a working point of phi equal pi over 2 will be equal to 0. So this one will also be equal to our noise, and we can simplify this equation a little bit. Delta of NA minus NB will be equal to alpha e to the power of 2g plus sinus hyperbolic squared g, sinus hyperbolic sinus squared g. This e to the power of 2g comes from replacing the cosine and hyperbolic cosine and hyperbolic sine with e to the power of g here. And noticing that this entire term is just hyperbolic sine g plus hyperbolic sinus g squared. hyperbolic sine g plus hyperbolic sinus g together be equal to e to the power of g. Then that is the square, which gives us a 2. Okay, so what we have left to get the sensitivity is to take the derivative of our intensity. I'll write it again. Okay, I'll write it again. Just remind you the sensitivity is phi at phi equal pi over 2 to be equal to the noise of NA minus B equal pi over 2 and derivative of A minus B respective to phi at, everything on this side is at, right? So we saw that A minus B equal sinus hyperbolic sine squared g times alpha squared. By cosine, yes, cosine phi. So the derivative equal, there's also a minus here. No, no minus. So now there's a minus. Minus sinus phi. Sinus hyperbolic squared g times alpha squared. And at and b at phi equals pi over 2, just equal minus sinus hyperbolic squared g minus alpha squared here squared, and overall the sensitivity would be alpha absolute value alpha squared minus sinus hyperbolic g divided by alpha is just alpha. This is like square root, because this is what? Square root of absolute value squared equal to g. I mixed them up. That's what happened. I took them in the wrong order. At the top, delta phi mean that phi equals pi over 2. At the top, it's square root of noise, so it's alpha hyperbolic squared equal to g plus sinus hyperbolic squared g divided by the value of squared minus hyperbolic sine g, right? Now, if we assume that alpha is very, very large, we can we can ignore this sinus hyperbolic term and be left with absolute value alpha e to the power of g divided by squared or e to the g 1 divided by absolute value alpha, which 1 divided by absolute value of alpha was the sensitivity that we found to the normal Mach Zehnder. And we see that if g is negative, or more likely if we actually measure the correct quadrature, measure the perpendicular quadrature, we'll see an improvement by the amount of squeezing that we did g. So this is the basic of squeezing enhanced interferometry. This is what they did in LIGO. Really, this is what they did in LIGO. They have the port which they use a very powerful laser, and then they have a second port which they feed squeezed light into through it. And then they basically do an interferometer and check the change in the space-time, basically. What is the time? 6:47. Okay. I won't do a C11 because I didn't do it yet, but I'm just going to show you that two squeezers can interfere and why we need the phase. I will do that and then I'll finish, and if anyone cares, they will talk to me about group theory after class. Because there is some interest, because we said that Mach Zehnder is SU2 interferometer and two squeezers are SU11 interferometer. Why do we use SU and SU2 and SU11? That's a question for group theory, for the mathematicians. Alright, so now we're going to do a very simple experiment. This is the wrong marker. We have a box generates squeeze state, another box that generates squeeze state. Then we have a pump that's filled on both. Then we have some beam with a phase component in it. Now what we're going to do it better. You're going to put the phase component on the pump, just because. Okay. Means that the first term generates A goes to G A plus Sich G dagger, and the second generate GA plus e to the I phi Sich G A dagger. Right. I'm not going to do anything complex, so that will take a lot of time. Be very quick, just go over point. So let's see. So we want to transform every A here, basically input, construct them one on top of the other. So just put the output of the first into the output of the second, the operator of the output of the second. So what we'll get, A out, well, this one is much better, will be cos, hyperbolic cosine G of, I put the first term, cos G A plus Sich G dagger, and now the second term plus e to the I phi hyperbolic sine G of cos G A dagger, note because it's A dagger, so it's the complex conjugate of it, plus Sich G A. Overall, this will be equal to cos G squared A plus cos G hyperbolic sine G A dagger, and from the second term we'll get plus e to the I phi hyperbolic sine G hyperbolic cosine G A dagger plus e to the I phi hyperbolic sine squared G A. Well, keep it going here. We get A cos squared G plus e to the I phi sine hyperbolic sine G plus 2, not 2, cos G sine hyperbolic sine G of 1 plus e to the I phi A dagger.
Sinh square, right?
What? Well, sinh square. Oh, yes. Always miss those. So we see here, very simply, we can see here two different options. First of all, when e to the I phi equals -1, hyperbolic cosine squared minus hyperbolic sine squared is equal to 1. So we have the A, and 1 minus 1 is equal to 0. So if the phase is perfectly perpendicular between the two squeezing, we just get back the input, which is the A, the annihilation operator of the input state. But if they're in phase, which means that this e to the I phi equal to 1, we get cosine, bless, we get hyperbolic cosine squared G plus hyperbolic sine squared G, which is equal to 2 cosine, sorry, I'm going to write it down like that. Hyperbolic cosine squared G plus hyperbolic sine squared G equal to cosh 2G, and here we'll get 2, so 2 cosh G sinh G will be not cosh, sinh 2G. So we just, if we're in phase, we just got a crystal or a squeezer that is twice as long, twice as powerful. So we see that we can do some sort of interference pattern between those two. An interference pattern is all that we need to make an interferometer. So while I'll not fully develop it now, I think you can believe me that this is an interferometer, just two squeezers. It's called an S1 interferometer. Maybe next tutorial we'll talk about complex two-mode quadrantures, and then we'll see the real power behind this thing. Unless you have any questions, I think we're done. Yeah, so just to summarize the tutorial, we looked at the Mach-Zehnder, then we saw, okay, the output basically measured quadratures, and the noise of the quadratures that we have mostly come from the interference of the vacuum state from the unused port. So if you can squeeze the quadrature in the output, in the unused vacuum port, we can also squeeze the noise of the quadrature that we get on the output of the Mach-Zehnder. Like that, improving our sensitivity by using squeeze line. And it's used with long experiments. Modern gyroscope also use quantum effect to improve the sensitivity, LIGO, etc., etc., etc. I think this is the long job. Well,
שאלת ההשערה.
what? איך היה בכנס?
איך אתה בוחר איזה מעצרים לקבץ ולהתחיל?
Oh, that's a good question. Well, first of all, we need to remember that the axes are chosen arbitrarily, so the squeezing is also chosen arbitrarily. The one that you want to squeeze is the one that you want to measure. That's the best answer. Yes, that's the answer. The one that you want to measure is the one that you want to squeeze. Or vice versa.
אז נגיד מה שאבי הראה לנו עד עכשיו זה רק מתאים ל-X, רק X יגדל ו-Y תמיד יקטן.
When I wrote it like this, I made an assumption, a few assumptions here. I assumed that G is real. That means that the pump, if you walk at the frame of the pump, the rotating waveframe of the pump, means that our modes, our A dagger, are in phase with the pump, which means that the pump stretches the real quadratures. You can try to do X equal A plus A dagger. There's one half here, but who cares? And then you will see A plus A dagger. You know what? Let's do it. It's just a second. A plus A dagger. This is the X quadrature. You see cosh G. I'm going to use it for a second. Cosh G A plus sinh G A dagger plus cosh G A dagger plus sinh G A. since we have a plus here, cosh is e to the power of g plus e to the power of minus g. Sinus is a minus between them, so it will be e to the power of g, a plus a dagger, e to the power of gx. So this one stretches the real quadrature and compresses the imaginary quadrature in the rotating wave frame of the pump. Because real and imaginary are abstract that we chose.
היה בכנס.
עשור.
לא יודע. אבי אמר היה מלא בלבולי קוונטית.
היה כמה הרצאות מאוד מעניינות, היה כמה הרצאות ממש לא מעניינות, אני אגיד את זה ככה.
הוא בעיקר התלונן על ה...
לא, נכנסתי... הייתי עייף, פחדתי סשן אחד וישבתי בו עד הסוף. כאילו כל פעם. פחדתי סשן אחד וישבתי בו עד הסוף. לפעמים בעיקר זו שאלה של איזה סשן לבחור, זה האם מישהו מאיתנו רוצה ואני צריך להיות נוכח בגלל זה, או האם יש הרצאה מאוד מעניינת. למזלי הרבה פעמים זה ישתלב, כי אנחנו עושים פגישה קוונטית, זה הרצאה שלנו, זה הרצאות מעניינות לדעתי.
אבי אמר שהיה שם איזה מרזנדר שרוצה... לא מרזנדר...
הוגה מנדל.
כן, שיהיה סביב העולם.
מה?
לא יהיה הוגה מנדל.
הם עשו...
אינטרפרומטר.
מישהו עם אנדרי בראון וטוויסט שדיבר על זה. על מה אנדרי בראון וטוויסט עושים. דיברנו על זה בקורלציות. אבל הם עשו להרחיב את זה עם קוונטים, זה לא היה לי כל כך מעניין דווקא. אני נורא נהניתי... עשינו הוגה מנדל?
לא.
דבר עם רגע, עשינו הוגה מנדל, זה מאוד מעניין.
רגע, אולי כן.
יכול להיות שכן ואתה לא זוכר.
אני אצייר את זה ואתם תגידו לי אם עשיתם או לא. יש לך בים ספליטר שנכנס לך one photon enter for here, one photon enter for here, they're indistinguishable. We just leave it at that for now, and then you will see that the output are either two here, two here. This is called bunching, when you have two separate states which give either a bunch coupled here or coupled here. They won't go one and one. This is Hogan Mandel, which shows some properties of